Okay, and please, well, this is the first lecture for the course of mirror symmetry by John Alexander Cruz Morales from the National University of Colombia.
Okay. So thanks, Marina, for the introduction and also for the invitation to give this series of lectures here in Madrid, but I am in Bogota, the power of technology. And thanks everybody for coming, right? So let me start with the topic of the first lecture, which is this, try to discuss this question, what is mirror symmetry? And I will actually give some incomplete and biased approach to this question, but it will be kind of the uh, background discussion for the rest of the course. And so let me just start saying that this mirror symmetry, or this question about mirror symmetry, actually fit in this I can say emerging field called the physical mathematics. This is an expression actually introduced by Greg Moore and other people, used to say that there is this kind of mathematics, this kind of math, actually inspired by physics, in particular, inspired in string theory. Okay, so there is some papers you can find on archives and on the web, many papers about this physical mathematics and the kind of mathematics we can find. Actually there is a recent paper by myself where I try to discuss this physical mathematics from philosophical point of view to see what actually is this thing. But okay, but the important thing for today is this state theory business, right? So let me start saying something about some physics, very general. So we have a string theory. So in the string theory, we have that the space-time should be a 10-dimensional manifold. Okay, so the space-time should be 10-dimensional manifold. Okay, so locally should be the following. So locally it should look like so. Locally should looks like the following. So you have the usual space-time, for the special relativity, the Johann-Minkowski space, and you have another manifold X here, and this X should have the following property. So X is compact, actually it's small, should be very small, right? Riemannian manifold. Manifold. Actually, dimension should be 6. Dimension of X should be 6, right? And there is two properties for this thing. So the metric X is Ricci flat, and also X has a complex structure. So the complex structure such that the Fertian class is 0 and the metric scalar with respect to this complex structure, right? So this actually implies that this X is a Calabi-Yau manifold. It's a Calabi-Yau trifold. It has real dimension 6, and so the complex dimension should be 3. Good. So what is mirror symmetry? Roughly speaking. So mirror symmetry is the following thing. So we actually want to discuss these things. So it can be thought, so it's an equivalence between, you know, between the physics of string theory, the physics of string theory, on two different Calabi jobs. Okay? Then will be roughly speaking, symmetry. I will explain what actually this means. And in fact, actually, I didn't say that, but I should say that this is a kind of duality. It's a duality. It's an example of a duality in physics. So the two different physical systems, but giving the same information. And this idea of the duality will be quite important later. Good. So what is the thing? So we have these two theories. So these theories, these string theories, such as string theories, string theories. So how um, can be described by the so-called n equal to superconformal field theories. So because this is a big overview, so it's not really somehow important what actually mean this to do, but it's some kind of supersymmetry there. But what important is like so in two dimensions. In two dimensions. So superconformal field theory. So I will use this notation. So what is important is like that in the 80s, Dixon and Lerige, Buffer, and Warner. Okay. So they noticed the following thing. They noticed that sometimes this Calabi falls come in pairs. They will call it pair X and Y. Says that so you have this string theory. There is some essentially four types of this string theory. So the type 1, type 2A, type 2B, and the heterotic, right? That's somehow something in the string theory. But what they actually say here is like that the A type, so the observation by Dixon and the other authors was that the A type is corresponding to the two A type string theory, superconformal theory of X is equivalent is equivalent is equivalent of the is equivalent to the B type superconformal field theory Y, and vice versa. So the B type superconformal field theory of X is equivalent to the A type superconformal field theory of Y. That's the thing. So in particular, there is this observation. So in particular, because for the was it is actually the first mirror symmetry observation. If you compute the Hodge numbers 111 for X. So what you get is the hash number 21 for Y. And of course, the 21 for X is the 11 for Y. So this is somehow the first observation about mirror symmetry. So how the Hodge diamond, you get the Hodge diamond of X and you rotate 90 degrees and you get the Hodge diamond of Y. That's the thing. And that's actually probably the name mirror came. It's like looking the Hodge diamond through the mirror. So in this sense, we call this XY a mirror pair. A mirror pair. Okay, perfect. Okay. So in general, in fact, what you have is, or what we have is that, you know, the AI type theory, string theory of X should be equivalent completely to the 2B type string theory for Y. But okay, but I have to make some important remark because usually, you know, for mathematicians, the this equivalence or this mirror symmetry is not about this A type and B type theory. It's about something A and B, but a little bit different but related. So let me just clarify this, which is sometimes confusing in the literature. So okay, so let me just remark that we have the following thing. So in 1988, so I will try to to name all the people who contributed in the field, but of course, again, my list will be incomplete, and I apologize if I don't mention some important people and important works. So in 1988, Witten introduced the notion, introduced the notion of introduced the notion of topological twists for topological. Okay. So what was the thing? So you have this superconformal field theory, or actually a supersymmetric sigma model. So you have a supersymmetric sigma model, right? This is of a supersymmetric sigma model. But somehow this supersymmetric sigma models can be understood in terms of superconformal field theory. So it's okay. So if you have the supersymmetric sigma model, so we have two twists. So we can obtain from this data we can obtain two topological twists. Okay, called the A model and the V model. The A model of X and the V model of X. Right? And that's somehow for mathematicians and actually in the literature, essentially mirror symmetry will be some equivalent between this A model and B model. So the question is how these A of X and B of X are related to the A type superconformal field theories I mentioned before. So question, so how this AX and BX okay, relate to the A type, A and B type superconformal field theories I mentioned before, right? So this is very interesting. So it turns out that it turns out that the AX and BX, this topological twist, actually compute certain limits called the Yukawa couplings, and this will be actually important in mirror symmetry story. The Yukawa could even be there, Yukawa couplings. For the superconformal, theories. So, in particular, the equivalence between the superconformal theories implies the equivalence between the A model and the B model, right? That's the thing. So that for this, lecture, so we consider mirror symmetry in terms of this A and B model, so the topological twist defined by Witten, right? Maybe some small remark, which is a little bit funny, that is this topological A model. This topological twist, the A model actually tell us about type 2B theories, the string theory, and the V model tell us about type A2 and 2A string theory. So that's the thing. Good. So what is important with this A model and B model in terms of the mathematics of the geometry? This is the main remark here is like the A model only depends on the symplectic structure of X. And the B model only depends on the complex structure of X. Okay? Good. So we can rephrase this duality in physics. We said, okay, this duality between superconformal Bird theory, so this equivalent between the A and B model. So we can rephrase this in the following terms. So mirror symmetry will be for us, and that's for me very important thing is like duality. So duality between symplectic and complex geometry.
May I ask a question? Is it okay, or shall I
Sure. No, sure, you can do it if you want.
say something else about the string theories? So why is it called A or B? Does it have to do with what kind of geometry, or is there a duality there in the fact that the A model tells you about the type 2B string theory? Yeah, can you say something else?
So why they are called the string theory A and B? Actually, the name A and B for the string theories is as far as I know is actually is came before the A and B in the topological twist. So I guess that the actually the in the topology the Witten actually, so the names A and B in Witten's work probably came actually from the relation with the string theories of type 2A and 2B.
Okay,
Why actually they
or the
publish this name
opposite.
type 1, type 2A, 2B, and heterotic? I don't know.
Okay, thanks.
Yeah. So why they put these names for the four string theories? So I don't know.
Okay.
Good. So okay, so we have this so we have this duality, so between symplectic and complex geometry. This is really so at the end of today, I will discuss another uh, type of dualities of this type in mathematics. So that will be interesting to see that this particular relationship between complex and symplectic geometry, actually we call it mirror symmetry, right? That's another important point. I didn't say that, and it's also when we talk about mirror symmetry, we also kind of we are not really careful in the terminology. It's like, let me say that another remark is the following thing: like actually the Calabi-Yau's manifolds, in particular three-fourths. We are now focused on three-fourths. So typically, come in families, right? So in fact, mirror symmetry is a duality not between two individual Calabi-Yaus, but between families of Calabi-Yaus, right? So mirror symmetry, in fact, mirror symmetry, in fact, somehow it's an equivalence, of families of Calabi-Yaus, right? And actually the corresponding corresponding model spaces match. Okay, so match at least locally. I don't I don't I won't talk about this aspect of mirror symmetry, but in fact, one of the thing is like, okay, so you have the space of, this, you have the complexified uh, Keller model space on one side, so you have the complex model space on the other hand, and then mirror symmetry actually is kind of isomorphism between these two model spaces, at least locally, around some maximally unipotent monodromy point. And the map relating these two things is the mirror map, and the mirror map is an important object in mirror symmetry. It's a little bit mysterious, still is mysterious. So I don't want to, discuss this part because this is more important for the Calabi-Yau situation, and I want actually focus on the Calabi-Yau situation. So I started the story in Calabi-Yau situation because that's the story of mirror symmetry. So mirror symmetry started in Calabi-Yau situation, but the topic of this lecture is not the Calabi-Yau case. So that's what I don't want to actually emphasize a lot in this discussion about this um, mirror map and the model spaces story. But that's an important part of the mirror symmetry pictures of it, right? And in fact, uh, understanding this mirror map, I think that's the big, problem in mirror symmetry. So I understand why we have this particular map that connect these two geometries. Good. So, but so far I just mentioned some kind of very physical motivation. So, but the question is, okay, so why mathematicians are take care about or care about mirror symmetry? So why mathematicians do care about mirror symmetry? Good. So 35 years ago, exactly, there was the following paper. So there's Candelas de la Osa, Green, and Parks in 1991. So they use mirror symmetry for tackle the following problems. So to predict the number of rational curves in the quintic threefold. So this was actually a long, I mean, actually they solved a long-standing problem using that. So the number of degree one was actually known by in the 19th century, I think by Sugar probably. The degree two actually was computed in the 80s by Katz, Sheldon Katz, so he got the number. But for the degree three, actually the problem was open, right? And there was some actually some this story actually is written in some papers, but I was actually told by Manning about that there was this congress where people, so there was a group of mathematicians, so they give some number of the degree three curves, and there was Candelas de la Osa presenting their work, and so they gave the numbers. The numbers actually didn't match. So people thought, okay, probably so physicists they are wrong as usual, so no problem. But after a month, so the group of mathematicians, so they realized that they had a problem in the code, so they corrected the problem, and they got the same number as physicists. So that actually was really important because in Candelas de la Osa, they don't only compute the degree three, but also they predict other degrees, the number of rational curves. And that's actually the beginning of the story of the mirror symmetry in mathematics. So what you can actually, this story about the quintics is well written in the literature. So the important thing for me is the following: what they did. So what Candelas de la Osa they did. So the problem of computing this rational curves you can consider as a problem of um, in the A model. And what they did actually, they convert the problem of computing this A model numbers in computing something in the B model, which was easier to compute. And then using the mirror map, they could get again the number of rational curves. So let me say a little bit more what they did. So what they studied actually was the following. So they studied the quintic reform, and his mirror family. Why? See, because it actually was a one parameter family. So actually they know how to consider the family before. So there was a work by, I think it was Pleasant and also Candelas and another people. So they found a way to construct the the mirror family. In this case of the quintic, what you have to say to do is you consider this Fermat is actually the word family. So you have to take some quotient by the symmetries, which is this C5, and then you get some singularities, but the singularities are crepant, so you resolve the singularities, and then you get the mirror family. So they know how to do it. So they have a recipe to construct this YT, and also not just for the quintic, but for other Calabi-Yau threefolds. And then what they do was they compute the Yukawa couplings. The Yukawa couplings FA and FB. So the Yukawa coupling for the F, for the B, for the A model, this FA, is related to the number of rational curves, and the the Yukawa coupling for the V model was actually computed using period integrals. So geometrically, the A model has to do with counts of rational curves. And the V model has to do with period integrals. For this, for B. This kind of thing. So this alpha is an element of H3, and omega y p is the holomorphic volume form. So with some normalization, so holomorphic volume form. Good. So they actually compute these periods, and then using the mirror map, they get this number of rational curves. I don't actually. Today I won't say more about this, but next time when I talk about mirror symmetry for finals, I will back to this picture of mirror symmetry. But so that will be somehow the main approach to mirror symmetry I will consider for the final case, right? So in this sense, so you can consider mirror symmetry as the following. So this number of rational points leads to the development of what is called Gromov-Witten invariance and Gromov-Witten theory, at least genus zero Gromov-Witten theory. So you have genus zero Gromov-Witten theory. And you can think that this is kind of mirror to Hoche theory. So here you have this Gromov-Witten invariance, maybe with some enumerative meaning, like in the case of the quintic, and in the other half you have periods. So you can think of mirror symmetry as this kind of duality, right? So duality between Gromov-Witten invariance or Gromov-Witten theory and Hoche theory, or just periods, right? And that's somehow, from this enumerative point of view, that's the main aspect of mirror symmetry will consider. Here I put zero because there is some higher Gromov-Witten theory, and there should be some kind of mirror picture also for them, but that's not really important for us, right? The thing is, like, you can, so you say that we can, you can do this for Dorer, Calabi-Yau falls, actually Morrison, compute Gromov-Witten invariance for other Calabi-Yau falls, using the same idea of Candelas de la Osa, so going to this Hoche B model side and compute the periods, right? And in fact, you can, as a mathematician, you can say, okay, what happened with higher dimensions? So in physics, trifolds are important because are the ones appearing in the space time. So for string theory, but in principle, we don't have any restriction in mathematics on the dimensions. So let me just say that mirror symmetry can be extended. So this kind of duality I described between complex and symplectic geometry And this duality between Gromov width and invariance and periods can be extended to arbitrary dimensions. So the duality holds, or, or should hold, it's better to say so, or can be extended, to higher dimensions or dimensions, not just higher, because also you have a duality in dimension 2 and dimension 1. So into other dimensions. Particularly, for example, if you study the elliptic curve case, it is quite interesting to see what happened, right? That will be actually topic of another lecture series to study use the mirror symmetry for the elliptic curves, because what is interesting in this case is that the mirror map is essentially the J function, the J invariant. So it has a lot of arithmetic properties. So actually, it's also motivation to say that there is a lot of arithmetic information behind mirror symmetry, which could be actually very important from the mathematical point of view. Good, but yeah, that will be for another occasion. So good. So let me back for a moment again to physics, right? So we have the picture we discussed about the mirror symmetry it was actually incomplete because I didn't consider an important piece, which is the following. So so there is there is one important piece of the mirror symmetry. You know, that we haven't discussed yet, which is actually uh, namely the idea of the brain. This D is for Dirichlet. So Dirichlet brains. So what actually is this? So mirror symmetry should be extended to consider these D brains. What is actually this D brain? So I thought actually that we are considering two-dimensional theory. So you have a string actually when the string propagate in the space-time. So what we get is a surface, right? This is called the worldsheet. So the surface actually traced by the propagation of the string in the space-time is the worldsheet, and actually the worldsheet can have boundaries, and these boundaries are the D branes. So these branes actually so nice. They are a nice boundary condition for the superconformal field theory. So that's something we have actually to to consider. Okay. So so we were actually trying to discuss what will be the mathematical formulation for the mirror symmetry, the use of mirror symmetry. So we said, okay, the mathematical formulation could be this kind of relationship between complex and symplectic geometry. This is very vague. So what could be mean is that for the symplectic side, we can get this Gromov-Witten invariance, and then for the complex side, we can get this periods, this Hodge theory. So there should be this relationship between Hodge theory and Gromov-Witten theory. So now we can ask, okay, what will be the formulation, or what will be the proper mathematical formulation of the mirror symmetry if we actually consider the branes? This actually gives this introducing these deep brains actually give us one of the two main approaches to mirror symmetry. So I want to mention them. So the first one actually is what is called the homological mirror symmetry by Kontsevich. So trying to find this formulation. So homological mirror symmetry. Good. So in his ICM talk, 1994. So actually Kontsevich proposed that you want to understand this mirror symmetry, actually this equivalence should be actually understood as some equivalence between categories. So concerns actually propose that mirror symmetry should be an equivalence of the categories. Okay. Actually, if you are kind of philosophical, bias like I am, so this is really interesting because there is this very, for me, deep approach to the geometry here that is actually the right notion of space should be found in a categorical level. So you really want to, so you can think of this, the question behind this mirror symmetry and these things actually is what is the space? Probably one of the, big questions. So it's not a new question, actually. I guess even the Greeks, so they actually ask this kind of thing. So, and then there is this categorical approach to geometry. Actually, I think not just started with conservative, but started with, it's kind of part of the Grothendieck heritage, I guess. And it was quite important in the 80s in the Russian school. And that somehow you want to understand the idea of the notion of space. So you should go to the categorical level and study somehow how to capture this, the right space with some kind of category with some properties. And I think this homological mirror symmetry is part of this program to understand geometry and to understand spaces, in fact, from the categorical point of view. So what actually Korsevich proposed was the following. Say, okay, you have in one side you have symplectic geometry and you have complex geometry. So for a symplectic geometry, so associated to symplectic geometry, you have we have the derived Fukaya category. This is also something in the literature people usually call it Fukaya category, not the derived Fukaya category, but for mirror symmetry, in fact, we need some kind of derived construction, which is not actually the derived category in the strict sense, because the Fukaya category is not a category in the strict sense. It's kind of A infinity category, so but doesn't matter these technicalities today. So, but the point is that you have this category, or this categorical object from the A side, and from the B side we have associated to the complex geometry side. We have the derived category coherent chips. Again, this Fukaya category is a little bit, it's not an easy object. There is no good, definition of this thing. I mean, a lot of studies about the Fukaya category. And the coherent chip is something more, understandable. And so mirror symmetry means in this context, if you have a mirror pair, this is a mirror pair. So you consider the Fukaya category or the derived Fukaya category. Let me just write this Fukaya category of X that should be equivalent to the derived category of coherent chips of Y. And the other way around, so the Fukaya category of Y should be the derived category of coherent chips of S. This is as a triangulated categories. Or even more, even as DG categories. Right. Let me just put it as a triangulated categories. Okay, that's really interesting. That's a very, very nice and elegant formulation, but it has, I think it has problem. you don't, so there is no, this homological mirror doesn't tell us how to construct the mirrors, right? I mean, what they say that if you have something and you know there are mirrors, so they should be derived equivalent. But we don't know how to construct, I mean, we don't know, you start with a manifold Calabi-Yau X, how to construct Y. So homological mirror symmetry doesn't say this thing. You just say that there should be this equivalent, right? So however, the introduction of these the brains came with some more, geometric approach to mirror symmetry. So the other approach, the other approach is due to Stemminger, Yao, and Senslow, 1996, and it's actually known as the SYZ conjecture. And actually, this gives more a concrete geometric interpretation for the mirror symmetry, so how we can probably get to construct the mirror. So let me just say how we can get this thing briefly. So D-branes are in fact submanifolds of the spacetimes, or submanifolds of the spacetime. Okay. So we started saying that the space-time is 10-dimensional. So there is this, we say that there is this, looks like this product, right? So we can split the D brane into a product of a submanifold in R13 and X. So we can split a D brane into a product of a submanifold 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 R13 and 1 on X. That's it. Good. Okay, so let's just focus on submanifolds on X, right? So there are two particular types. There are two particular types of submanifold of X. Manifolds of X. Okay, on X of interest. So we have this, so the holomorphic D branes. Holomorphic D branes. Okay, sorry. Holomorphic D branes. Okay. This is some holomorphic submanifolds. With a holomorphic line bundle. And the other ones is what the most important in this story for us, the special Lagrangian D branes. So there are special Lagrangian submanifolds. Manifolds. with flat U1 bundle. Okay. Okay. So now, so the tangent space, to the model space of the special Lagrangians, the model space of special Lagrangians in the Lagrangians deformations, of a special Lagrangian submanifold M. M. So here Y is the mirror to X. So this thing is actually the H1 and with our coefficients. So on the other hand, the model space of flat, the model space of okay. So the model space of flat U1 bundles or one connection, sorry, one connections, modulo gauge equivalence is the torus, okay, on M is the torus H1 MR quotient by H1 with integer coefficient. So actually we need that in order to get the right dimension for the model space, we need that the dimension of the H1MR is equal to n, right? So what is the thing? So this actually suggests the following. So this suggests the following. This suggests that X consists of a family sorry, it's a dual to a family of a special Lagrangian, special Lagrangians, or special Lagrangian tori. On Y, and that's actually this the SYZ conjecture. That's actually the content of the SYZ conjecture. So let me just formulate the conjecture more precisely. So SYZ. Okay, so the conjecture said the following: if X and Y are mirror pair, Landau-Ginzburg in false, no need to be true false. In false. So that exceeds some vibrations. So there exceeds vibrations. F D and F. Let me just call F check on TV. So they both have the same basis. So you can see this is like we have here B. We have X here, you have Y here, right? Here is F. And let's check. Right? Okay, whose fibers in the special Lagrangian with general fiber. And torus. So torus and dimensional torus. So additionally, furthermore, the vibrations are dual. Dual in the sense that you take somehow fiber over V. Um, Fiber. Are not singular because so they are dual. They are not singular too. Are not singular. Okay, the vibrations are dual in this sense. Okay, good. So these are the three bigs actually. So you want to ask the question, so what mirror symmetry is? So the big three ways actually to answer this question, the most popular approaches in the literature are okay, mirror symmetry should be this enumerative mirror symmetry I mentioned at the beginning. So the relationship between Gromov-Witten invariance and periods, and with all these enumerative meaning this would enumerative consequences. The other should be okay, homological mirror symmetry. So there is a lot of work in homological mirror symmetry. There is these big groups, big machinery in homological mirror symmetry. And the other thing is was the conjectures. Again, there is big groups and there's a lot of people actually working in that direction. So there are these are the three main, I guess, approaches to mirror symmetry for the Calabi-Yau. I mean, so far we have been talking just about Calabi-Yau, right? Of course, there are other approaches. I mean, I didn't mention this, but there are other approaches like, for example, Batirev mirror symmetry. Batirev mirror symmetry. There is this Gross-Sieber intrinsic mirror symmetry program. And also these two are also quite important. There's also a lot of work in that direction. So you want to consider higher genome mirror symmetry. There is this approach by topological recursion. So these all people doing this kind of work, topological recursion. So from physics and from mathematics. So there is a right. So there is a lot of literature in this thing. So you wanted to show you or to discuss with you that there is these three big approaches, actually from historical point of view, but also conceptual point of view for the mirror symmetry. So you can interpret mirror symmetry as this enumerative quality or this Gromov-Witten quality or this equivalence between categories, and otherwise is a conjecture. So there you can ask naturally, okay, they are related. As far as I know, there is some recent work by, I think, by Nick Sheridan and his collaborators. I hope I am not making a mistake, but they try to like homological mirror symmetry with a Hodge theoretical enumerative mirror symmetry. It's supposed that if you have homological mirror symmetry, then the relationship between gamma width and period they should hold, and also S was Z. But it's not really clear. I mean, at least for me, how these three pictures actually are related. Which one implies the other, or if they are actually equivalent. So, for example, if you have so it took some time. For example, Candelas de la Osa, they actually prove the mirror symmetry for the quintic, Giventhal, and also Zhao and his collaborator, they proved the mirror symmetry for the complete intersections. And I think the homological mirror, that was in the 90s, and homological mirror symmetry in this context actually was proved by Nick Sheridan in his PhD thesis in 2011 or something like that. So it's not actually completely clear if one of these, you have the mirror as a as a Hodge theoretic, Gromov with duality implies the homological mirror symmetry or the other way around. There is a question in the chat, so good. Okay, so good. So there was just a question.
Yeah, sorry, it's just me. I need to go. I'm sorry.
No, it's okay. Good. So okay, so that's the that's the that's the thing. So for us actually it's really important the following questions. So it's really important the following question, and it's how about how about uh, how about other manifolds beyond Calabi-Yau, right? So there is this claim by Orlov. You can find it in his paper, Landau-Ginzburg models, D-branes, and mirror symmetry. And you see that actually the title of this paper is really, really, connected to the topics of the series of lectures, right? I almost actually copied the name for for this lecture. So in this paper, actually, Orlov claimed the following: so mirrors should exist for all types of varieties. So in particular, you have uh, um, for manifolds or varieties of general types. So there should be some picture of mirror symmetry. So this will be kind of interesting. But there is an additional thing that will be important in this extension. And in fact, this is what I will discuss in the following 5 lectures. And when you go beyond Calabi-Yau, so you want to extend the geometry. So in these cases, we need to extend the geometry. Let me just call it extension, extend the geometry. And consider what people call, and I like actually the name, consider geometries with potentials. And in this geometry with potential, actually, it's a way to talk about Landau-Ginzburg models. These Landau-Ginzburg models are kind of geometry with potentials, right? So I am kind of interested in this thing when X is a Fano. If X is a Fano, then with the topic of lecture 2. Okay. Sorry. That'll be the topic of the lecture too. And also there is something, if X is a holomorphic symplectic non-compact holomorphic symplectic manifold. And that will be somehow the last lecture. Or maybe lecture 5 and lecture 6 will be the topic of this. So that will be, so I am interested in the geometry with potential, this Landau-Ginzburg model, in particular when we want to study the mirror of a finite manifold, or when we want to study the mirror of certain non-compact holomorphic symplectic manifolds. And the hope is that we can probably extend this picture to the heat-sink systems. That's what I will discuss in the last lecture, right? Good. So that's for plan of the lecture, but I have some minutes, so 15 minutes, something like that. And I want to discuss a little bit more about mirror symmetry. Let me say something more. So because mirror symmetry is more than what I said, right? So I began I I started saying that okay, that the mirror symmetry is a kind of duality in in physics that has some uh, counterpart in mathematics, right? And it was very particular between two very particular physical theories, and it came with very particular duality in mathematics. So the point is that there are other dualities in physics that actually also have the name of mirror symmetry. So let me just say that. So there are other, I want actually, somehow some of these dualities I want to discuss here are related with the topics of the last lecture, but I won't actually enter into this in the last lecture, but it's a really interesting story. So there are other dualities, that also let me say the name of mirror image, a kind of mirror image. Good. So far we have discussed what is understood as a two-dimensional mirror image. So because we started with a two-dimensional theories, you remember? So we said, okay, there's this superconformal field theories of dimension 2. So we are in dimension 2, and usually what people call mirror symmetry is this duality in dimension 2. But in physics, actually, also we can have the following. So in physics, there is a notion of three-dimensional n equal 4. This is n for the symmetry, supersymmetries in the theory. Supersymmetric quantum field theories. And in this picture, actually, in this setting, actually, interrogator and cyber, so interrogator and cyber, propose what I call the so-called three-dimensional mirror symmetry. Three-dimensional mirror symmetry. Three-dimensional mirror symmetry. And actually, this three-dimensional mirror symmetry that identifies two theories, T and T, and T check. what do they do? So for any of these 30, we have, for each of these 30, we have two spaces. So here you have a 30T, you have two spaces. So for each 30, for each, for each 30, we have two spaces. Two spaces. So the Higgs branch of the space, and let me call it this M mesh, and the column branch and C. Both of them are hyperkähler manifolds, in fact holomorphic symplectic, but they are hyperkähler manifolds, or holomorphic symplectic. So Higgs branch is something that you can define mathematically. Column branch is more difficult, so there is no, okay, there is an approach to define under some condition the column branch from the mathematical point of view. This is the work by Braverman, Firkenberg, and Nakajima. So in a series of papers, they define mathematically this this column branch, at least for a very particular case when you have a gauge theory, which is of the cotangent type. They propose some definition for this space. And then, so mirror symmetry, the three-dimensional mirror symmetry should be, three-dimensional mirror symmetry is that if you take the column branch of the theory, the theory T, it's actually isomorphic to the Higgs branch of the dual T check, and the dual and the opposite, so the Higgs branch of T isomorphic to the column branch of T check. Okay, good. That is very interesting because somehow these manifolds in general are somehow manifolds. Actually, there are varieties. They are because they can have singularities. So they are what is called symplectic singularities, and then so there is a study in mathematics of the symplectic singularities and the symplectic resolution singularities. So Nakajima-Cougar varieties are one example of these things. So there have been a series of observations there are some relationships between some kind of this kind of symplectic resolutions, and in mathematics this is called the symplectic duality. So
Alex, may I ask a question? This
sure.
isomorphism, what kind of isomorphism is that? I mean, at the level of
It's
one
a hyperkähler manifold.
A hyperkähler manifold. Okay, good.
Hyperkähler, yes.
Yeah, go.
Yeah. So this is called actually symplectic duality somehow, and this is and there is somehow some there's some kind of there is not actually a precise definition what a symplectic dual is in mathematics, but there is a bunch of expectations. And let me just say that there is this one example, this baby example will be the following, is to have some idea what happened. So you have a finite group subgroup of SL2, right? And then you have X is this quotient singularity, right? So you have the Y is the minimal resolution. So this is the minimal resolution. This is Euclidean singularity, right? But that's actually symplectic resolution. So it's an example, symplectic resolution. So in particular, if you take gamma to be the cyclic group, right? So what you have is that the claim is that the symplectic dual of this thing, the symplectic dual is the cotangent bundle of this TP minus Y, right? Right. That will be the three-dimensional somehow mirror of this resolution of singularities, right? So there is also a lot of work in this direction. There is this very interesting paper by Webster and what's the name? Joe. So they have a very nice survey about this three-dimensional mirror symmetry. There is a lot of work in in this direction, especially by the Opencroft School and his collaborators. Right, you can ask, okay, what will be the relationship between three-dimensional mirror symmetry and two-dimensional mirror symmetry? So there is actually a recent paper from 2024 by Conan, Leun, and forgot the other author. So the title of the paper is Three-Dimensional Mirror Symmetry is Mirror Symmetry. So they actually try to study this three-dimensional mirror symmetry, this duality, as in terms of the two-dimensional mirror symmetry. So that's really interesting to see what is going on here and how actually the three-dimensional mirror is related to the two-dimensional mirror in that sense. So, but there is another actually uh, version for mirror symmetry, where we actually there is this very nice and beautiful work by Kapustin and Witten in 2007. I think it was around 2007, and actually they interpret a version of the geometric Langlands correspondence in terms of physical duality between four-dimensional field theories, okay, with some symmetries, so n equal 4 supersymmetry. Okay, this is very interesting because we know we have two-dimensional, three-dimensional mirror symmetry, and this four-dimensional approach, right? That will be actually this. So we can think of this mirror, this geometric Langlands as a kind of four-dimensional, a kind of four-dimensional mirror symmetry, right? The thing is like the supersymmetric Jan Milk's theory in four dimensions. For a pair of Lagrange dual groups. They're related by the so-called S duality. So this S duality will be like, the version of mirror symmetry. So two-dimensional mirror symmetry is T duality. This is S duality will be like four-dimensional mirror symmetry, and somehow it is a way to see the Langlands, geometric Langlands, right? So there is something interesting like this, in three-dimensional mirror symmetry, we talk about the 3D n equal 4 theories. And the point is that this 3n equals 4 theories appear as boundary conditions on 4D n equal 4 super Germans. So these all pictures are actually connected. That's interesting. Because you have, somehow M4 Yalmir theory, so you can see the boundary, instead the boundary condition, you have the 3D n equal 4, so you get probably three-dimensional mirror symmetry, and then using this Cannon work, and so you can see the two-dimensional mirror symmetry as actually two-dimensional mirror symmetry. So how to connect all these pictures, that will be really interesting, but I think this is still open. I mean, I think not just mathematically, but also, I mean, probably physically, from the point of view of physics, there's a lot of work, but I think from the point of view of mathematics, there is not that much is done. And the last lecture, maybe when I talk about heat shield system, I want to propose a kind of wild set of expectations about that what I am presently doing. So I will back to this at the end of the lecture. So let me just make this summary, to summarize it. So what is mirror symmetry? So the mirror symmetry depends. So you have two-dimensional mirror symmetry. Two-dimensional mirror symmetry. So it is probably SYZ conjecture, yeah, right? So symplectic complex duality. You have three-dimensional. So you have the 3D mirror symmetry in physics. So here's in mathematics symplectic duality. You have four dimensions, so you have S duality, which is somehow geometric Langlands. And of course, you can ask, okay, what is one-dimensional mirror symmetry? But there is actually, so we can think of in one dimension, it is the Fourier transform. So the Fourier, and somehow there are people actually claiming that, saying that, okay, mirror symmetry, in fact, it is the Fourier Laplace transform. In a certain sense, it is, right? I mean, somehow this, um, all these pictures actually are kind of elaboration of this, in certain sense of this whole duality, which is actually the Fourier transform, right? So that's the way I propose, to answer the question what mirror symmetry is, and then tomorrow, no, the next time on Wednesday. So I will start just focus on the mirror symmetry for Fermi manifolds and telling you what exactly I mean by mirror symmetry in that context and make it more, details. So today was just a big overview. I mean, the topic is really, really big. So it's more than 40 years of mathematics and physics with very active groups and very good and strong people from the side of physics and from the side of mathematics working on this thing, right? So actually, before the talk, I was checking archives, and I saw a paper by Michalkowski about the Landau-Ginzburg model for Fano threefold. So I should have new material for my lecture of Wednesday. So, but I want to say that this is really active and just still, I mean, the question of what neurosymmetry is still an open question. So we have different approaches, and we have different approaches depending on the dimension and depending on what actually we want to compare. But but what actually to have actually an answer, we really need to go deep into math and into physics. So thank you.
Thank you, Alex. Thank you very much. Maybe we can react or clap somehow. Well, thank you.
There is this, yeah. Okay.
Okay, so let us stop the recording and then give a space for some questions, some extra questions, if anybody has.